Good afternoon, everyone. I am Naomi Schimberg, and I am from Providence, Rhode Island.
I'm Sophia Liu, and I'm from Dublin, California.
I'm Chad Cerruti, and I'm from Fort Lauderdale, Florida.
I'm Sonia DeSange, I'm from Fremont, California.
I'm Ian Hong. I'm from Nevada, and together we are the GRACE team. Now, GRACE stands for Gravity Recovery and Climate Experiment, and it is a mission consisting of twin satellites tasked with taking detailed routine measurements of anomalies in the Earth's non-uniform gravitational field. The image on the left here is a gravitational model of Earth, with the areas in red being more massive and the areas in blue being the least massive. Now, take these kinds of measurements to detect and understand the processes that drive changes in Earth's mass distribution over time.
So GRACE is a collaborative mission between NASA's JPL, Germany's Aerospace program, and University of Texas' ICESaT, which is where you're sitting right now. The two twin satellites were launched in March 2002 from Russia, and originally the mission was only going to last for 5 years, but more than 15 years later, the twin satellites are still in orbit.
So, how does GRACE work? Unlike other Earth-observing satellites, like take ICESaT for example, which uses a laser altimeter to directly measure the Earth's surface, the two main instruments of GRACE are the satellites themselves, which are connected via a microwave ranging system. So if you picture a mountain, and this is GRACE A and this is GRACE B. When GRACE A reaches the mountain has mass, so it's attracted by the gravitational pull, and the distance between GRACE A and GRACE B increases. Now, when GRACE B reaches that same mountain, it's pulled by its gravitational force, and the distance decreases. And so there's this constant oscillation of the distances between GRACE A and B. And since we know the distance, we can then mathematically infer the gravity and the mass of what's below. However, GRACE is also always experiencing accelerations that aren't due to gravity. So the accelerometer on board eliminates all non-gravitational accelerations. Finally, GRACE has a GPS system, which is communicating with the satellite or the constellation of GPS satellites thousands of kilometers above, and that tells us where GRACE is and when it is there. And the time aspect of that data is what we use in our project.
All right, and so as you can see here, GRACE has given us a very detailed map of the Earth's gravitational field. Before GRACE, we had a very coarse resolution map. There wasn't very clear data. It was very generalized data. Whereas with GRACE, we now have a very detailed, very high resolution map of the Earth's gravitational field. However, GRACE is not only useful for gravitation, but it's also useful for many other models, such as a hydrological model. So, which is the hydrological models like lakes and rivers of the Earth, and also models drought scenarios. So, for example, the California drought, you can see over time this is GRACE data. The red areas represent areas with like decreasing moisture, and so that comes from decreasing soil moisture and decreasing water reservoirs and such. GRACE is also useful for noting geological changes, such as after earthquakes when there's a large mass redistribution. It's also useful for glacial thickness, knowing how thick ice is on the polar ice caps and such. And also for sea level rise, knowing how high the sea level is for climate change.
So this is our project. Our objective was to use real GRACE satellite data, analyze it, and compare it to model data. So we achieved our goal by splitting it up into two sections. For the first task, we used real GRACE satellite data and compared it and looked at it from a global perspective. And for the second task, we used model data and looked at it from a regional perspective.
So like Sonia said, our first task took a global perspective to analyze GRACE's global coverage. And within that task, we had three main objectives. The first one was to generate ground tracks given latitude and longitude data of GRACE. And the second was to count the number of times that GRACE enters a certain box, which we would decide the specifics of. And given how many times GRACE enters that box, create a heat map which would show how frequently GRACE visited those boxes. And the data we used was from 2002 to 2014, and periodic longitude, latitude points of GRACE.
So for task one, we decided to delegate the work and split it up into 4 different sections. This is sequentially. First, we needed to plot the ground tracks, and then we needed to create a global room. And then after that, we needed to create a counter to count how many times the ground track would pass through each individual bin within the sprint. And then once we had that data, we then needed to create monthly survey registration maps. And here on this diagram flowchart, each output ends up being the input of the following code. And so because we needed the codes to work together cohesively, it was really important that we communicated possible.
So I plotted Grace A and Grace B's ground track on these 2 graphs. And a ground track is basically a path that a satellite takes and it's projected on the Earth. And for the first, for the red graph, I used red to represent Grace A's path, and then for Grace B, I used blue to represent path, Grace B's. And then I plotted Grace A and Grace B's ground track on one graph. And due to the scale of the image, the 2 paths look so close together that they appear purple. However, if there were to zoom in, you could see the 2 separate paths. For the first 2 Grace satellites, for the 2 Grace satellites, when there's more mass, the first satellite will speed up and put more distance between the 2 satellites. So I used the Himalayas as an example. The 2 satellites have more distance between each other because there's more mass in their mountains. And for Death Valley, since it's more flat, there's less distance between the 2 satellites. But the distance is only 0.1 degrees. So it's difficult to see if it's because my ground is.
So Sonia accomplished our first objective within task 1, which is plotting the ground tracks. And now the second objective is the counter. But before we can make a counter, we would actually have to define which areas we would be counted in. And Chad and I worked on this function, which is creating a box. And we had to think a lot about boxes. How big would the box be? How many boxes would we have? And what would define the edges of the box? So we decided to use a 3x3 degree box. And the maxes and the edges of the box would be defined by maximum and minimum longitude and latitude points. And the outputs of our function could be passed directly to Ian's function, which would begin the counter.
So my role in task 1 was creating the counter. And the purpose of the counting function is to determine how many times Grace has the opportunity to take measurements of a certain area of Earth. Now the function does this by running through all of these satellite positional data we're given, starting with the oldest data and moving forward through time. Now what we are interested in is finding out how many times Grace visits the area. And the function accomplishes this by counting how many times Grace enters the box. This is necessary because if we're simply to count how many data points would lie within the box, we would end up with an excess of data because of how Space takes time to pass the box. Up here, you can see one of our boxes. The boundaries are defined with green, and the red points are where Grace entered the region. If we were to graph, as I said before, if we were to graph all of the data points that would lie within the box, we would end up with a really red box and way too many data points. Now, using the list of areas provided to me by Chad, the program ran through all the data we have to find out how many times this satellite visits every specific part of Earth. Of note is that calculating visits this way is extremely processing intensive. To calculate visits for over 1 year to be 7,200 boxes under our grid of Earth, we have to analyze 6,191,507 data points for a total of 89,158,158,608,000 individual calculations. We had to leave the code running for 11 hours to finish all of those calculations, but in the end, we were left with a count for all of these boxes that was in passed to Sophia for further analysis.
So once I was able to receive the data from his counter, I was able to create maps of the surveillance differences over experience time. And on the bottom of the diagram is the flowchart of basically the steps that my program took to create the maps from the data. And this is what this is a map from June 2008, and you see on the bottom of the scale goes from dark purple to very bright yellow. the darker representing areas where Grace happened fewer times that month, and then the light yellow representing where Grace happened many times that month. And if you notice on this particular graph, there is a prominent purple band across the equator, as well as purple spots above and below the equator. And this is a really great contrast to pole, where it's very bright yellow because that's where the satellite captures it most often. And this is due to Grace's near circular polar orbit, and it's also affected by the fact that a 3-degree mercury box takes up a unique sampling area on the pole as compared to on the equator. And then, using these maps for 2008, I compiled all the monthly plots into an animation of the yearly progression of Grace's orbit, and the changes in the month are due to both Grace's non-European ground track as well as its orbital precession. Yeah, we'll talk about that. So yeah, it changes on there. You can see the purple spots, and sometimes it's less purple spots.
Right. And so we ran into some challenges during the first part of our project. Mainly the first one is that all of us really had a lack of coding experience coming into this. So we needed to learn the basics essentially in order to complete our project. And then so because of this, then we had a lot of trouble converting our thoughts then into code. So for example, for the box issue, we knew that Grace would measure, say, 6 or 7 times in a single 3-degree by 3-degree box. We'd only want to count that for 1 time, and we knew this. It was just a matter of putting that into code that was the issue. And also, because we were working in small groups, we needed to make sure that our functions were compatible with each other. And so, for example, we needed to make sure that Naomi and I's outputs would then work for ENT.
So another challenge we faced was dealing with special cases. And special cases are times when we select areas to analyze that the code doesn't know how to handle. One of those special cases is when we put our box directly on the North Pole. As you can see here, the blue box is the box we're analyzing, and this is the North Pole. Now, that is what we look like up there. But translating that to a rectangular coordinate grid is not an easy task. Because of the way code works, there are some cases where it's possible that the areas that we choose to analyze either extend beyond the 360 by 180 degree coordinate grid we have laid out, or in fact fit in a very interesting manner. While we voted to not use these cases in our final code as they were unnecessary, accounting for them would make our code more comprehensive because we would be able to analyze these boxes that extend beyond the grid.
And one of the difficulties that I faced when I was training the math was choosing the perfect color scale and color scheme. And this was important to creating a good map because I wanted the data that I was trying to show to be communicated well to an audience and as well as show accurately.
So we accomplished task 1, moving on to task 2, which instead of taking a global perspective, zooms into 24 specific locations on the globe, which you can see in this graphic. In addition, while task 1 used data directly from the Grace satellite, task 2 used this Grace satellite data in addition to model data, which is AOD data and GLDOS data, which is taken every 6 hours and every 3 hours. Now, what is model data and why do we use it? Both of these sets of model data are components of the hydrological cycle. GLDOS data is the Global Land Data Assimilation System, which is a land surface model, and AOD data is atmospheric and oceanic de-aliasing, which is atmospheric and oceanic model. Both of these models are mathematical models based on what we know about various climate processes and field experimentation. So now, using this model data, we can compare it to Grace data. And we could assess whether Grace's sampling frequency, that is how often Grace visits a certain point on the globe, is sufficient to study climate processes. And then on a more abstract level, we could study the climate data variability using the AOD and GLDOS data.
And so in order to model these and to compare them, we need to plot them together on the same point. And so up here is the AOD process that we used. If we just replace AOD with GLDOS, we did the same process in order to plot the two. And so we started with the AOD data, we started with the time. We also started with our own Grace data that we used. And essentially just plotted them. However, it wasn't that easy. There were some discrepancies between the data. First off, the AOD and GLDOS data, Their data calculations began on January 1st of 2008, whereas our data, our GRACE data began on January 1st of 2000. So we needed to make up for this time and add about 252 million seconds to our GRACE data in order to compensate. And then also our AOD and GLDAS data was given to us in hours in 3 and 6 hour intervals, whereas our GRACE data was given in seconds. And so we needed to do a simple conversion in order to convert the AOD and GLDAS data to seconds. And essentially we just took those and plotted them together. And this, we ended up with 48 plots for the, or 24 AOD and 24 GLDAS plots for each of the placings. There are 2 right here. On the left is the AOD data. The model data is in red, and the GRACE data are the black diamonds. The AOD data model is short-term high variability. And then on the right is the GLDAS data. The GLDAS is in purple. Again, the GRACE is in the black triangles, and GLDAS model is more long-term. And also, if you see the boxes, the blue box on the left and the green box on the right, those are month markers. We model our data over the course of a year. And so each box represents the start of a new month, just for ease of looking at data and understanding it.
So the graph on the left here is the same one from the previous slide, and it is the yearly data over the AOD and GRACE data. And throughout the entire year, you can see a lot of red that extends beyond the black diamonds, which is the GRACE data. But we wanted to take a closer look at January, where there is quite a major peak right there. And we found that this was directly related to a tropical cyclone that developed in the northern Australian area, which is really what we should have done. And you may also notice that there's not a lot of black diamonds at that peak and at the dip right after it. And it shows us that GRACE alone is unable to detect this weather phenomenon.
But in other cases, like this Bangladesh monsoon, we see that both the GRACE data and the model data accurately showed what happened in our environment. So we can see from a UN report in 2008 that the periods of most intense flooding were in the summer and early fall months. And we can see this direct correlation with the graphs. We see both GRACE data, again, in the diamonds, and the GLDAS data shows that the highest magnitude of climate data variability was in these months. What you just saw were 2 out of our 24 locations where we presented with model data. And you also saw how the model data had a higher sampling frequency than the GRACE data, because the model data was either every 3 hours or every 6 hours, whereas GRACE visited these sites, say, every several days. And we only have model data for these 24 locations. So, and we see that model data predicts it more frequently. So for a future task, we could come up with some way, some new satellite, or additions to existing satellites to increase GRACE's data volume to increase both temporal and spatial coverage of our globe.
So now we know that the frequency of GRACE data collection is inadequate without the pattern of model data like AOD and GLDAS. But when you rely on the model data sources, GRACE doesn't get full, complete, and independent data that is enough to be self-sufficient. But the frequency issue can be resolved by altering the orbit, but then that would hinder the spatial data. Another solution would be making a constellation of satellites or attach trailing satellites to existing satellites.
What we learned. So in addition to creating a final project, we learned even more on the way to creating this product. First was programming and improvement. So as we mentioned before, our outputs had to be capable with the inputs of next. And we learned a lot about how to communicate effectively. In addition, we learned about model data. So I think going into this project, all of us just assumed we were going to be looking directly at GRACE data. But we were taught how, when used in conjunction with model data, we could learn even more about our climate.
And also, so we learned how to use real-world data and how to incorporate that into our project. So in a perfect world, all our data would have the same time interval, same units. They'd work together. But we don't live in, or we do live in the real world, and so data is not like that. And so therefore, like, for example, as I mentioned before, we needed to convert our hours into seconds in order to make our data work, and also change the time that we started our data at in order to make sure that our project would work. and also we need to understand our results, essentially. So when we go through your project, and we need to understand what we were coding and what we were receiving out of that in order to further our project and understand what we were doing.
And the last thing we learned was all about the different functions of GRACE and how it can be applied in environmental science. But also, apart from this, we saw GRACE's interventions in how to be used in the future because we did not yet have a very high efficiency. You're welcome. And before we end this presentation, we want to give a special thank you to our awesome mentors, Archana and Corinne, who have been great this past 2 weeks, very patient in teaching us the ICESaT coding. And I would like to give a special shout out to my brother because it is his 18th birthday today, and he's here watching me. So thank you for that.
So how did you go about learning programming? Like, what kind of way of thinking do you think you learned the most from the programming? If you know what I mean. Or yeah. Or what was your favorite part of programming? There you go.
So my favorite part was seeing how all of our functions could cooperate with each other. So when Chad and I were making our grading function, we were like, wow, we're just splitting up the world into a bunch of boxes. But then when we passed it to Ian, and he was able to count how many times Grace visited those boxes, it was cool to see that in action. So I guess the logical flow of step A to step B to step C was the most exciting part of it.
I think when we first started coding, especially the first one, I was super excited to do it because I thought it was super cool. I felt like I was in one of those flat movies, wherever I was coding. I actually manipulated my terminal area to be black with the green text or something. So yeah, I think coding is really cool and it's a skill that a lot of people should try to learn.
Yeah. Great. Join me in thanking the great Yeah, the next innovation is Lunar Exploration. The great seems like their globe.
I was trying to explain the
Hello, we are the Lunar Exploration team, and this is our project, Research on Mars, Understanding Life Under the Sun, also known as Romulus. My name is Taylor Harwood.
I'm Phoebe Ball. I'm Izzy Torres. I'm Casey Thomas.
I'm Charlie Britt. And I'm Adrian Garza.
So why should humans go to Mars? Humans will have an opportunity to do things on Mars that robots cannot do. For millennia, humans have thrived on the frontier, and it drives us to create new inventions that improve the lives of everyone in society. Our goals for this mission are to bring humans to Mars and back to Earth safely. We also want to test in situ resource utilization, so that way we would be able to establish a more permanent settlement on the Martian surface. We would like to search for the probability of life as well, because that can have significant impacts in fields such as biology and pharmacies here on Earth. Our habitat is designed for 6 astronauts, but our requirement was to make it capable of supporting up to 14 in the event of an emergency where a crew was stuck and stranded on the Martian surface. We want to prove that we can successfully produce rocket and rover fuel, as well as water, oxygen, and other consumables that will be needed by the astronauts on the surface. We will leave behind a fully functioning settlement for other crews to use if necessary. We will also set up stations that can be used to continue to monitor the Martian surface after we have left. We will bring back at least 100 kilograms of Martian regolith, and in doing so, we will be careful to ensure that we do not contaminate the biospheres of either Earth or Mars. We had several assumptions in this project. We had 7 SLS Block 2 130-ton launchers. These can take up to 43 tons to the Martian surface. We had a budget of $1 billion per year for 5 years, and we assumed that we already had a pressurized rover and a communications satellite at Mars. The SLS launcher on the far right is the one that we used for this project. The Martian environment is the most similar to Earth's on our solar system, but is still drastically different. It only experiences 38% of the gravity we do here on Earth, and it has less than 1% of the same atmosphere that we do. And its atmosphere is primarily made up of carbon dioxide, which makes it inhospitable to humans. Mars also has drastic temperature variations. On a summer day, the temperature can range from -73 degrees Celsius to 20 degrees Celsius in the same day. Mars also does not have much opportunity for solar panels. Solar panels are not very efficient on Mars due to its farther distance from the sun and the large dust storms that occur. These are things that we have to keep in mind when designing our habitat. I will now hand it off to Phoebe to talk about our science objectives.
Thanks, Haley. Okay, so since this is the first planned Mars mission, we had to meet several science objectives. The first of which is the search for life. So now we know that Mars, at some point in its past, had liquid water on its surface and had conditions suitable for life to form. So therefore, our science expeditions will search for fossils and other signs of past life. Now currently, the Martian environment is very harsh. However, there are organisms here on Earth that can survive similarly harsh environments, for example, extreme temperatures, extreme pressures, and radiation like that on Mars. Now, the search for life on Mars will not only lead to breakthroughs in medicine and science, but also will help answer some overarching questions. For example, is life unique to Earth, or can it form wherever the conditions are correct? Also, there's a theory that suggests that life on Earth may have originated on Mars. Okay, our crew will also study Martian geology. In addition to studying the composition of rocks, our crew will also look at volcanic activity and hydrothermal vents, which can create pockets of warm areas beneath the surface where life can thrive. Our crew will also study the Martian atmosphere. Mars has had a much thicker atmosphere, however this was stripped away by solar wind after the planet lost its magnetosphere for unknown reasons. By studying the atmosphere, we will gain information that will help with entry, descent, and landing techniques, and also in situ resource utilization, which I will get to in a moment. And lastly, simply by living in a habitat on Mars, we will be gaining insight into the viability of a future habitat on Mars and the colonization of Mars. By studying the crew's health and troubleshooting problems with the habitation modules, the future settlements on Mars will be better equipped to live on the surface for longer durations. So now, as part of the study of the viability of habitation on Mars, we will be using in situ resource utilization. So now this process converts the Martian atmosphere into rocket propellant. And this rocket propellant would be much too heavy to bring with us from Earth, and it will be used to get the crew off of the Martian surface. So this process uses a Sabatier reaction to convert the carbon dioxide in the atmosphere and 6 tons of hydrogen brought with us from Earth into water and methane. This water is then split into oxygen and hydrogen. The hydrogen is cycled back into the system to be reused, and the oxygen and methane can be used as rocket fuel and manned vehicle propellant. So now we used a decision matrix to choose our landing sites. We ranked 5 different landing sites based on their habitability and ability to meet our science objectives. Our top 2 sites were Utopia Group, where there was recently discovered a liquid water lake 3 meters beneath the surface, and Northeast Syrtis, which is one of the 3 candidates for the Mars 2020 rover. So now we chose to have our landing site on Northeast Syrtis. There are large areas of smooth terrain which would be great to put our habitation modules. There are also ridges that could have been formed by hydrothermal activity, and carbonate structures, which could have been formed by liquid water springs or surface water, so this is a great place to search for past life. The area is also geologically interesting. It has a history of lava flows, and there are areas of layered sediment conveniently exposed for study of Martian history. Here is a map to give you reference as to where Northeast Service is located. You can see the Curiosity rover is there for reference as well. So now here's a diagram of our launches. As you can see, all of our habitation modules are launched in separate launches due to their large mass. There's a fourth launch reserved for the in-situ resource utilization and the greenhouse. And all of these modules will be pressurized and ready for the crew to live in them before the crew arrives on Mars. And the in-situ resource utilization will complete its process and communicate verification back to Earth before the crew launches to make sure that the crew is not stranded on the planet in the event that the system will not work as planned. The crew will then launch at the next launch window 2 years later. They will spend over 500 days on the Martian surface and return to Earth, leaving the habitation modules on the surface of Mars for future use. So now here's the overall structure of our habitation modules. This image was rendered in CAD by Izzy. So you can see that 2 of our modules have inflatable ceilings, and our third module does not. The inflatable ceilings are 4 meters high, adding height to our already 2 meter tall rigid base. The third module, the dorm, is 3 meters tall. Now, these are launched separately, so they must land in far away from each other so they don't risk crashing into each other upon landing. So therefore, rovers will tow them together and they will be connected with inflatable hallways, and the pneumatics on the wheels will raise and lower the modules to ensure that they are level and at the same height. So now all the inflatable parts on our modules were modeled after the beam module of the International Space Station. So now with inflatable modules, obviously radiation and debris penetration is a concern. However, recent studies on the beam module have shown that radiation levels are very similar to the non-inflatable modules on the International Space Station. Also, the beam module has not leaked any air, and if it were penetrated by debris, it would slowly leak rather than bursting open. And lastly, our rigid walls of our habitation modules are made of aluminum honeycomb. This material is very, very strong, yet is also a lot more lightweight than solid aluminum. And it is commonly used in the aerospace industry, for example, on the Saturn V instrument units and the Japanese S-series rockets. Now I'm going to pass it off to Izzy to give you information on our science module.
Okay, so our first module was our science and technology module. Naturally, it had all the equipment required to meet all of our science objectives and technology demonstrations. So first off, we need all the tools necessary for machine repairs. We're going to have rovers on the surface, and we may have problems with our habitat, and so we're going to need to be able to correct those errors. This will include items like drills, soldering irons, and even 3D printers. We also need the necessary equipment for field research. We will be doing month-long EVAs, and after we leave the spots that we travel to, we want to be able to continue collecting data. We can do this by leaving behind weather stations that will then communicate with the habitat in order to continue giving us long-term data about the Martian surface. We'll also have necessary equipment for the in-situ resource utilization. And then finally, we'll have all the necessary science lab equipment in order to determine the composition of samples and whether or not they contain biological compounds. There's also a second floor to the science module. This is where we will house all of the exercise equipment and the medical stuff. So we have a treadmill, a bike, examination table, radiation evaluation equipment, everything necessary to make sure that the astronauts are healthy throughout the trip. Finally, a bit away from the habitat, we have a separate inflatable greenhouse. This will be a technology demonstration. As a second mission, most likely we'll need to use large-scale agriculture in order to prevent using too much food that's just brought from Earth. So you can see that is divided into 3 sections for the plants. You have the first section, which is just for Earth soil. This will mean that we need to take a lot of kilograms of soil from Earth in order to keep it running. We then have the Martian method, which is just using Martian soil and fertilizing it with human solid waste. And then we also have the hydroponics method. And then you can see that each of the sections will contain 6 different types of plants so that we can determine which are most viable. These were selected based off nutritional value and potential morale boosting capabilities. I'll now pass it off to Casey for discussing Module 2.
Thank you, Lee. I worked with Charlie on Module 2, where it contains the life support systems and the controls for it, and the life support systems support all the habitats. The life support systems can involve the environmental monitoring, atmosphere management, and water management. Atmosphere management balances and filters all of the gases that the astronauts are breathing and makes sure that it's safe for them to breathe. The water management system just cycles through all the water, making it safe for them to drink. And the environmental monitoring maintains pressure at around 14.7 psi, which is around equal to Earth's pressure. It also controls the thermal and humidity, as well as if there were any disasters such as a fire, it controls that. Aerocycling on Mars habitat is similar to the ICESaT aerocycling system. Initially we will bring enough resources to support the entire crew on a closed-loop aerocycling system. However, we are also bringing in-situ resource utilization systems, as we discussed, that will use the Martian atmospheric gases and convert them into resources that we could use, such as potable water, oxygen, and nitrogen. The water recycling system will use a water walls function. So the water walls are located inside each of the module's rigid walls. They're about 442 millimeters thick, and they're able to perform many of the life support systems using not that much space inside the walls, keeping it organized. They're able to process gray water and black water, remove carbon dioxide, revitalize oxygen, grow algae, which can treat the carbon dioxide that the crew exhales, and also provides some nutritional supplements. And it also provides thermal and humidity control. It also adds a layer of radiation protection to the crew. As I said, the water walls are situated around the rigid structures of each of the modules. It is biologically and chemically passive, and only uses a mechanical system to pump the water through each of the polyethylene bags, which are located around the system, and it uses forward osmosis to clean the water. Fire safety is very vital to the crew, so there will be smoke detectors in each module, and also in the ventilation systems. In the ventilation systems, they can decide whether there are any harmful air particles and then alert the crew of the air quality. There will also be carbon dioxide fire extinguishers located for case B and C fires, which are caused by electrical equipment and flammable gases. And then there will also be, in case of emergencies, the crew will evacuate to the airlock or to their EVA suits and then open the airlock for the burning area, which will then use Martian atmosphere to deprive the fire of oxygen, therefore burning it out.
So we were supplied with a 25 kilowatt nuclear reactor, which arrived on the Mars surface before the crew even left the planet. And this reactor was then buried half a kilometer away from the planned habitat area so that the crew would be not risking possible radiation from the reactor. It was buried by rover, and a 1 kilometer long extension cord made by NASA was put from the reactor to bring us back to the habitat in order to provide us with energy. There are two types of main radiation that we have to deal with on Mars. The first being solar radiation, which isn't as much of a threat because the Mars atmosphere actually shields the planet from most of solar radiation, though some does get hit. The other is cosmic radiation, which is more of a threat because it is pretty constant and it has the ability to pierce through the atmosphere and about a meter full of walls that it can just go through. And so to shield against that, we put, precisely 1,923 sandbags on top of the dormitory, the equivalent of 3 meters of protection in the room that they're going to be spending the most time in because they're sleeping. Waste disposal consists of a vortex incinerator, which is a NASA-designed waste disposal unit meant for Mars and Moon which is waste disposal. The vortex uses air to keep objects in neutral buoyancy so that it is able to hover in place, and then it uses other currents to swirl these pieces of trash around a burner, which it then incinerates. The vortex, since it uses fire, we decided that it would not be a good idea to put that inside the habitat. So we were trying to figure out a place to put it, and the best place was attached to the greenhouse outside. Because the greenhouse holding plants requires lots of carbon dioxide and creates oxygen, while the vortex requires oxygen and creates carbon dioxide, water, and ash, which can be used as fertilizer. That's a picture of the vortex. Yeah. The thermal protection unit protection system consists of a high-powered boiler, which will use energy from the nuclear reactor to heat water for showering or experiments, and has the ability to heat air to keep the habitat warm above the freezing Martian environment. And environmental monitoring consists of system monitors, which it's a tall pillar in the center of the room, which each side consists of a different system monitor that basically monitors the water walls, the thermal protection, the radiation, everything that's going on inside. It's the main unit, while the rest of the room holds more precise machinery that can control each sort of system more precisely. Now I'm going to pass it on to Adrian to talk about our living spaces.
Thank you, Charlie. Now, my partner Haley and I were focused on designing Module 3, which revolves around designing the astronauts' living quarters. Our astronauts are going to be living on Mars for a pretty long time, so we want them to stay comfortable. To increase how comfortable they are, we decided to include 8 main components in our HAB module. The first was a common living space where they could relax after a long day of work, an area where they could maintain their hygiene, a place where they could store, cook, and eat food, as well as a communication station where they could communicate with NASA, a bedroom, and an included workplace where they could conduct their research. Let's take a quick tour of the HAB module real quick. On the far left, you'll see the restroom and laundry room, followed by 3 dorms with 2 beds each, so the astronauts don't have to share. We go down the hallway. On the bottom right, we have the kitchen with some appliances that they can use to prepare their meals. And in the middle, we have the comm station with the included dining room table. And on the top right, we have the commons area. So let's go to the commons area. So we included a television there, just for some little entertainment for the astronauts, and a lounging space with a couch, 2 chairs, and a coffee table, so they can relax after some hard research that they're doing on Mars. If we go to the kitchen, we included 2 food cabinets, a dishwasher that, strangely enough, uses no water at all, 2 microwaves so they can prepare their meals, and a sink so they can clean up after eating. Now, we combined the dining room table with the comm station, so there's a table with chairs. And in front of it, we have the monitor and the media and comm center where they can communicate with NASA or participate with the public on Mars. Now, we're going to move on to the bathroom. And so here we have 2 wash basins and 2 washer-dryer machines, as well as a state-of-the-art clothes hamper where they can put their dirty clothes. On the other side of the bathroom, we have a storage cupboard where they can load in some toiletries that they'll need, as well as a lavatory and a nifty changing room where they can change and step into the shower so far back from the house. Now I'm going to pass it on to Haley Harwood so she can explain the rest on the 3rd module.
Thank you. So each of the astronauts will share a bedroom with another crew member. These bedrooms come with 2 loft beds, a storage space for each astronaut to place their personal items and clothing, as well as a desk and a work chair. These rooms are small, but they will give the astronauts personal space to relax after they have finished their work for the day. There will also be a partition that the astronauts can pull out, so that way they will have their own room for the time being. This will make the room smaller, but at the same time it continues to provide them the privacy that they need to continue functioning well with the rest of the group. One of the major concerns with designing this habitat module was actually the appliances. Most of the appliances we have here on Earth either use a large amount of energy or a large amount of water, neither of which are good when you're trying to use them on a different planet. For this reason, we had to research lots of new designs being proposed for new appliances. One of these includes a dishwasher that uses liquid carbon dioxide that can be continuously recycled instead of water, as well as a low-powered dryer that uses ultrasonic waves to dry clothes instead of the typical power-consuming heat. We also used a shower that can recycle the same 5 liters of water for 5 minutes. All of the appliances that use water will be connected to the waste disposal system, so that way the water can continually be recycled and reused by the astronauts. Overall, we managed to stay well under our budget of $1 billion a year and rounded out at a little less than $1 billion total. Each of our launches was also well under the required mass, but we also assumed that the SLS rockets would be provided for us, so that is not included in this budget. Here is an example of the detail that went into each of the budgets for the launches. This is launched through the Habitat module. In conclusion, we realized that there's a lot of untested technology that we need to go to Mars. So far, the greatest mass that we have landed on Mars is 2 metric tons. These habitats are far greater than that. Farther entry, descent, and landing technology will need to be developed for us to go to Mars. The SLS launchers that we are also using are still not tested yet, so that is another item that will have to be continued to be researched. As the Mars mission approaches, it is highly likely that we would have continued improvements in technology that we can incorporate in our mission. This is why we stayed well under the 43 tons that we can take to Mars for each launch, and it provides room for the incorporation of this. We did manage to successfully meet all of our requirements, including the cost and mass requirements. We also included triple redundancy for life support and mission critical systems, such as food supplies, oxygen, and capsules, and water. We would like to thank Dr. Mandel and Mr. Nix for helping us do this project, as well as the rest of the C staff for making this program possible. Are there any questions? Yes.
So if Vortex stops working, will the fire reach into the greenhouse?
Well, that is possible, but the greenhouse is not mission critical. The greenhouse is designed to simply test technology for future missions. So if the astronauts lose the greenhouse, the mission can still succeed and it will not affect them. Anyone else?
After all your studies about Mars, would you go?
Yeah.
I would.
Absolutely.
Yes.
Great. Join me in thanking the Mars.
We'll provide this.
Our next presentation is by
Starting. I like that we're this is 5.
Well, good afternoon, everyone. I hope everyone's having a great day. We are the Magic Brother Sons team, and I am Alex Webb.
I am Leah Otterstadt, and I'm from Stafford, Virginia.
I'm Erin McNulty, I'm from New Jersey.
I'm Avi. I'm from Chicago.
So we're going to start out with what exactly is magic?
Well, MAGIC is a division in CSR, and it is funded by NASA. And it stands for Mid-American Geospatial Information Center. And it's basically using Earth science to respond to emergency hazards. Environmental, there's flooding, hurricanes, and wildfires. And then our mentor, Mr. Porter, he also worked on the Columbia debris field, which tragically broke up in the atmosphere when it was coming back down to Earth, and there was a debris field path. The Deepwater Horizon oil spill right here is pictured, and then also the West Texas explosion.
Yeah, so our task was a little bit different. So from all the other presentations, we were tasked with creating a spatial-centric custom web application, which we use to visualize different types of data. So that data we would aggregate from different sources, from either GeoJSON files or REST endpoints from the internet, from different sources like different weather services by the United States, and they would be used to create layers on top of a map that we used that we generated through the Esri Leaflet JavaScript API. And so these different layers are supposed to create some sort of visual representation for us to analyze the data, maybe for any use by first responders, perhaps in case of flood response for MyApp and ICESaT, or really in any other case that we might see up there.
So what we learned, some of us had programmed before, but we had never done a web application, so we didn't really know HTML, CSS, and JavaScript that well. So we learned a lot about that, all of us. We really made a lot of progress in that. And particularly within the JavaScript, we learned a lot about mapping and about getting data from the web. Like, I know, at least for myself, I didn't know where the data came from. I just kind of saw it. But now I really had to go out and get it. So we learned a lot about that. And we also, we ran into a lot of problems on the way. There was bugs constantly. So we thought a lot about how to solve the bugs, and we thought through them, and we all became much better programmers because of it. And so, yeah, we learned a lot about displaying spatial data too, and how to display it, and what's the best method for displaying it.
Okay, so now we get into my application. I named mine flood response. And the reason why I want to do this is that meteorology is my passion. If I've had the opportunity to speak to you, most of you have heard from me that I love meteorology, and that's something that I want to do as a career. And so I also enjoy helping people, and with this app, I am able to help people in flood-prone areas with knowing exactly when and where floods are going to be. And I'm also on the flood response team, so I just kind of want to stay at the roots of the project. So the application components, we had to have some interactive sections, and so I have geolocation, and you can change your maps for topographic imagery, which is kind of like what you see on Google Earth. There's also streets, and you'll see the more when I demo it later on in the presentation. I also have a toggle switch, which has the flood outlook warnings, precipitation outlook for 6 to 10 days in advance in your area, radar, which is real time, and it's every 5 minutes, flood warnings, and also flood watches. So for the consumer, I came up with 4 questions that anybody would want to know if they are in a flood-prone area. And the first one is, what is my chance of flooding? How much precipitation am I getting? When might it flood? And are there any flood warnings or flood watches in my area? Now, this is just a look and a snapshot of my app. So the first is the precipitation outlook, and that allows the user to understand the precipitation within that 6 to 10 day period. And as you can see, the green right here, that is above precipitation, and that's shown by my legend. And then also the brown over there is also shown for the precipitation outlook. So the next step that I believe somebody in a flood-prone area would want to know is the flood outlook warnings. And those are seen in the purple right here. This was a couple days ago. And they can just understand further their chance of a flood in their area. So then we get into radar, and I think this is extremely important because that is where the rain comes from. And then the user for flood warnings and flood watches can also see in the final step, okay, so I have a flood warning or I have a flood watch. So, that's what you know before it starts to flood. And then finally, there's a geolocation button right there, and you can understand where you are compared to the rest of the United States with all the advisories, outlooks, flooding, warnings, and watches. So then we get into the app demo. Okay, so we start out and you're just looking at the United States. Now you can change it to anything you would like on the map. I prefer imagery, but that's just my personal choice. And there's instructions here. Now these instructions can help you out to use the app to its full potential, showing you step by step what to do. Now this is the toggle switch, and you can turn on the precipitation outlook. Okay. The flood outlook warnings, which are shown in the purple here. Radar, the flood warnings, and the flood watches. And that's just a snapshot of my map, and then you can also get the location. Okay.
So this is line 1.
Yes, thank you. So that just shows exactly where you are. And let's say you didn't know what that meant, so you can click on that, and it's 50% above precipitation for the next 6 to 10 day outlook. So this is my app. And I'm going to give it up to Alex.
Thank you, Leah. So I created an app called Driver, which stands for Drought and Rain Investigation, Visual and Environmental Representations. So the problems that I'm trying to face with this app are the increase in precipitation and drought that correlate with the transition in climate and higher temperatures, along with logistics of this mission. So basically the premise of this app is that with this transition in the climate comes short-term periods of flooding and long-term periods of drought. And so here you can see a screenshot of the app with all of the options toggled. And a couple of use cases for this app are, one, a national emergency responder looking to see where right now, which areas are most flood prone based on their drought condition. And also they can see in the near term, about 7 days, which areas are going to be most flood prone. So let's just jump straight into the app demo. So what first comes up is a description of the app and the button that allows it to enter. And here's a help button to give the user an idea of what options are best to see whether you want to look at current flood conditions or future. And so if you open this menu, one can see, like Leah, you can change the base map that would be best for viewing this data. And so if we jump straight into the data itself, we can see current radar precipitation and then drought conditions. And to see radar precipitation better, one can change the opacity or the amount that it covers what's below it with this slide bar here. And for forecast, this is most useful because it is a Esri rest endpoint polygon layer that actually covers the drought conditions. So it would be best to lower the opacity to allow better view. And if someone wants to see a closer view of one state, the user can select a state to look at. So this is Colorado right now. If you change back to the imagery base map, you can see that better. And specific coordinates can be inputted as well if the user wants to see an exact location. And legend here, this browser displays things differently. And I also have geolocation. All right, so slides and Aaron.
Hi, so my app was heat waves and vulnerable communities. So my app idea, when we were given the task of making an app that responded to some sort of weather emergency, this is my first time in Texas and in the summer, so I thought about heat, and I thought about how vulnerable communities might need a lot of help, and people would need to know where they are and if they have heat warnings, watches, or advisories. So yeah, my user base would be responders or people who are looking to help during these heat warnings. And so they would be able to look at my app and know where they needed to go and who they needed to respond to. So during the creation of the app, I faced a few problems. This was my first time making like a web app, so I learned a lot. It was really a great experience for that. And my main problem was finding data. So if you can see all the data on the right, that's a small snapshot of one of my data layers, and I had 4. So there was like thousands of lines in this one alone. So there was a lot of data to process. And it was hard to find it. I initially wanted to do homeless populations, but they're a hard demographic to keep track of. So there wasn't really any data in my county of where their homeless populations were most prevalent. And also so I used unemployment data instead. So if there was, I considered a county to have less resources if they had an unemployment rate above 16%. And one of the hardest parts for me was querying the data. So querying is just when you search for the data to look for specific things and comparing the different data levels. That's what I spent the majority of this week working on. So this is my app demo. So first, there's a little pop-up that tells you about the app. And like everybody else, I have a little thing that toggles between maps. So I have the current watches and warnings right now, only in Texas, on Louisiana. So that tells you this. Well, this is advisories because it's orange, as you can see from the legend. But that tells you that, and you can click and find out what it is. And then I also, this was from a few days ago. There was more. Last week there was heat advisories covering the contamination. But yeah, and then there's also highly unemployed counties. So throughout the states, it displays all of that. And then my last layer, when I was thinking about doing the homeless thing, I was considering putting shelters for each city so that responders could also know how to help with that. But since I couldn't find the homeless data, I couldn't do that specifically, but I made a demo of what the shelters would look like anyway, so this is for Baltimore specifically. But yeah, and you could tap and find out what it was. But really the main part of my app is the querying section. So you choose a state and you'll find there's 3 different cases that could happen. So one, in the case of Connecticut, there's no unemployed county, so the data is not really helpful for that. And then this is for Arkansas at the moment. No unemployed, highly unemployed counties have heat warnings or watches. And then finally, here's Louisiana. Takes a while to load. So as you can see, it displays the name of the counties on the side, and then it highlights the areas where the affected areas. So it's helpful for responders, and yeah, that's my. So I'll pass it off to you.
I promised on the last one, which is really fitting because I was working on this the latest. I think I finished it this morning. Different, a little different. I did a little bit different from everybody else in the group. While everybody was focusing on America, I went across the ocean, I guess, to where my parents are from in India, and focused on a place called Chennai, a city in southern India. And the reason for this was because in 2015, December 2015, there was a series of floods known as the 2015 South Indian floods, which displaced nearly 2 million people, killed over 500, and cost nearly $2 billion in damages, $3 billion in damages. And so it was one of the most catastrophic flood events in South Indian history. And one of the biggest, and one of the places that was the most affected was the city close to my hometown, close to my parents' hometown in Chennai, India, Tamil Nadu. And the most vulnerable, and what I realized is that the most vulnerable people in these areas were actually not those with obviously good resources and whatnot. They were the people in the slums of Chennai, because there are a lot of abject poverty going on right now in India. And so the reason I created that was to provide a greater spatial awareness for the first responders who could actually who could use my app to go in when future flood events happen, so that they could better analyze the situation and know where they want to target resources. Now, just to quickly clarify something, you guys might have remembered when Leia was talking about what MAGIC stood for, Mid-American Geospatial Information Center. And you might say, how is India Mid-American? Well, if you look at this graph real quick, you can see Maine over there in the top left, and an American territory, Guam, on the bottom right. So technically speaking, India is Mid-American. So, all this different. But on a serious note, the use case for this is mainly for, like I said, those first responders. And so my app displays a bunch of layers, one including a slum layer, which shows different slum populations, a heat map of those populations, where the greatest density of those slums are, overlaid with both relief center markers and the actual inundation levels in those levels specifically. And so this is supposed to provide those first responders with a better again, spatial awareness or visualization of that area, so they know where to target those resources. So I think now, actually, before I get started with the demo, I need to address a couple of challenging limitations. The first one is that India has awful data. Everything. So the problem with this is that the Indian data structure is very inconsistent, and so there will be different types of data. First of all, it's not very consistent. Like one REST endpoint that I can access from. There will be different types of data that you have to download or scrape, and I really want to thank my mentor, Mr. Porter, for helping me out with that, because there was no way I could have dealt with that by myself. And another thing was the conversion between Latin long and web replicator points, which isn't necessarily an India thing. I don't want to blame that entire country for one little issue. It really frustrated me throughout the entire process of building this app. And the other thing is the lack of real-time data. This event happened in 2015. I want to make that clear. It's not like the three apps that were demonstrated before, where it's constantly updating. It did only happen once, but the idea is to create a framework where if future events were to happen, you can just plug in the data, and as it comes in, and then you can visualize data that exists. So now I think I can quick demo of the app. So this is the splash screen that you see when you load the app. It gives a little bit of information about what exactly the South Indian crisis was, the South Indian flood crisis, and so when you hit View City, gives you a view of the city. And so in the top left corner, you see a sort of toggle sort of menu that pops open. And so this gives you a bunch of options. So down here, per se, you can start with the actual heat map of the slums. And so this gives population densities of where the greatest number of slum households are. And you can see in the bottom right corner, right there, the legend for that. So darker red areas like this will have a greater slum population, whereas lighter areas like over here will have a lower slum population, obviously. And so the other two layers that I've enabled on this, along with the slide that hasn't showed up for because Internet Explorer is really old, are inundated roads, which means flooded roads, obviously. And so that shows up in the layer like this, and the relief centers associated near those layers. And so you can basically zoom in wherever you want. And so first responders will be able to get an accurate depiction of where these relief centers are in relation to the inundated roads. This red circle marker that you see over here is just a marker for where the map is centered. And so the main feature here is the vulnerable districts, in which you can fly to specific districts. So for example, in Motherburn, there aren't many inundated roads, but there aren't also very many relief centers. And so if you were to go somewhere like Tinogar, you can see clearly that the inundation was great at much higher levels, and perhaps there weren't enough relief centers to accommodate slum population. And so these are the kind of things that I'm trying to look at when it comes to creating an app for first responders. Yeah, and so. Okay. Yeah, so we are now open for questions.
We have a questions here.
Is there a way that you could combine all of your apps to make like just one comprehensive response app?
We could collect all the data. I think with Avi's separate in India, that would be a little like messy, but we could definitely put all of our data together. It wouldn't be that difficult actually. It would be pretty simple. It would probably take us a day or two, but we could definitely put it all together. Yeah.
Actually, the only reason we might not want to do that is the reason we make individual apps, and I think that's what Mitch was looking for us to do, is because we want to visualize different data in different contexts. So if we were to have a bunch of toggles on the screen, it would be a little bit hard to visualize the data and how they're kind of related to each other. So like, for example, when it comes to droughts and precipitation levels, we want to see maybe how the climate is changing in a certain way. Whereas if you kind of combine that with other data, it might get a little bit cluttered. It's the only thing that we do.
You have another question, Phoebe?
So I noticed that your project seemed to have more individual work than the others, but I was wondering how much communication what went on between you guys? Like, how much did you collaborate together, and how much did you learn from each other?
Personally, I collaborated a lot because these guys are much better than me at programming, and so I went to them maybe every 4 minutes, like, this doesn't work. And they were probably the best group to work with, because every time they answer me, they fix my code.
Last question, yes.
How do you get the real-time data to feed into your code?
So as we talked about before, there's REST endpoints, and REST stands for representational state transfer. And so basically, it's a folder hierarchy that is populated by various sources. And I think a lot of us use government agencies because they have very consistent data in the US. And so they're the ones who are constantly taking the data and they're uploading new data constantly. And we simply have a link and it doesn't change. And you just put it in our code and then it scrapes the data from the quote-unquote REST end.
Great. So join me in thanking the project.
So we're not really good at making GIFs, so we made a GIF.
Yes. This is just our thank you to Mr. Porter and also to all of the people.
Yeah, and for all the people that helped us throughout this entire process, of the season, interns, and staff, and the rest of the people. And Leo, thank you for keeping up with us in the dorms when we were being really loud really late at night. Thank you again, Mr. Porter, for basically writing everything for me. Thank you, Alex and Leah, for keeping up with me when I was yelling in the middle of the night because everything was broken. There it is. Thank you, everyone.
Please join me in welcoming the astronomy team.
I'm James Bishop, and this is Asteroid.
Hi, I'm Maddie Springate.
Peter Trusses.
I'm Justin Wong. And I'm Sherry Patel.
Hey, so I figured we'd start this off with some history of MEOs. As you may know, the first one that was really discovered crashed into the Earth about 66 million years ago. And sort of the entire point of this is to sort of avoid the fate of the dinosaurs. Nowadays, with our current mass predictions, we think that an asteroid that has a diameter of even 140 meters could be very life-threatening, even on like a cultural level. And according to JPL's database, which started in 2003, there are now almost 8,000 said asteroids within that size constraint in our solar system, which is extremely scary, although it really considering how big it is. But, and 15% of those asteroids are over a kilometer, which is enough to cause serious damage to the percentage of humans on Earth. And it's really important to understand all of this so that we can sleep at night. Our specific project details how that research process works from telescope to asteroid. So just to kind of explain some of the grunt work we did, we were handed about 90 frames taken over 2 nights in late September of 2003 and told that there was an asteroid. The first thing we had to do is we had to find the asteroid in each frame, that is 90 frames. I'm going to mention that a lot later as well. I'm still kind of salty about it. So the first real difficult step is we had to correct some of the intrinsic problems using CCD imaging. It's an extremely sensitive piece of measurement that has to detect the number of electrons, so there's a lot of noise, as we'll detail a little bit later. The second step is we had to correct the atmosphere, and that required finding 25 stars in each of 90 frames by hand. Sorry, I want to keep mentioning that.
Before time you would have automated it. I have faith in you.
Yeah, so once we had 25 stars, we had to correct for atmospheric errors, which allowed us to compute magnitudes. And this gets a little bit complicated. I'm sorry, the cold I'm not tripping stuff. But we got, with visual magnitude we collected in our program, and out of visual magnitude, another kind of magnitude we mentioned further on, and we were able to calculate the absolute magnitude. And basically what that means, simplified, is we cancel out atmospheric factors and we cancel out distances and sort of its proximity in order to Earth, so we could only be looking at its brightness in order to find out its rotation, which is our ultimate goal in this presentation.
Okay, so everything that astronomers know about what they observe, they learn from the light that they're able to collect from the object. Trust me, astronomers choose to do photometry not because it's easy, but because it's hard. And if you see here, this is a CCD, okay? So, like I said, we collect all of our information from light. So, once upon a time, they used to use photographic plates which were really slow, and there's a whole bunch of things that make them inferior to CCDs, charge coupled devices, and these things are really helpful because they visualize the information and they have really fast encoding. So yeah, CCDs. The observations were made at McDonald Observatory at the 30-inch 0.8-meter telescope by Dr. Jeter Reeves. So the photometric process is okay. So what we use is a program called Asteroid, and it allows us to select an aperture tool which allows us to focus specifically on the source and then include some of the sky background. We originally decided the aperture of the inner source object area by looking at different graphs of this right here. As you can see right here, we have around a 6 aperture tool, 6 pixel aperture tool. That allows us to look specifically at the source, and then we have some background links. And just really quickly, I want to point out the measurements that we looked at. So as James was saying, we had 25 stars and an asteroid for each image. So that's what these are right here. You have 25 stars and all of that information. The biggest thing from this I want to point out is the source, the signal to noise ratio. During night 1, we had it wasn't a great night for observation compared to night 2. Night 2, we had twice the signal to noise ratio.
Okay, so initially all of our images were raw images, which have a lot of variation in brightness and color. You can see that in these raw images. There's like a shape right here. We don't want that variation to negatively affect our data. So what we do is we process our images. And so we process our images by first finding a master zero image, which is just a 0-time exposure image. And then we find a master flat. And then we take the master zero image that we found, subtract that by the raw image, and then divide that by the master flat to get around, what, 90 process images? So that's each raw image. Okay, after we process all of our images, it's time to find our asteroid. So we used a program called SAO DS9, and we put clusters of 3 images at a time in that program, and we did this thing called linking, which is just stacking the images and then playing them quickly so that you can see the asteroid. And so the reason that linking works so well is because asteroids are constantly moving in the sky in relation to stars. So it's really easy to see what we're looking for, which is a circular object that's moving in like a straight line, really straight line in the same direction. So you can see here our asteroid, which is moving 3 times, and a fairly straight line in the same direction. Okay, and after we find our asteroid in all of the images and gather all the coordinates for each image, then it's time to pick some stars. So the atmosphere changes in each image, which is why we chose 25 stars to compare the magnitude of the stars to the magnitude of the asteroid to eventually calculate the absolute magnitude of the asteroid. And so all of those little red dots are the asteroids that we chose, which is 25, and then 9 times. I memorized the star pattern. Shaylee and I would compete to see how fast we could do it. And then over here is the actual stars that we used. So that's the graph that we used. And we only used 14 stars. We got rid of the stars that didn't follow like the general trend.
Okay. So for some of our data, we use JPL's Horizon memory system. So basically, this is one of several large databases that provide data for astronomical observations. And we use this. This is really important for both pre and post observations. So pre-observations, we use this data, or Dr. Reese uses this data to figure out where the asteroid will be and when. And then post-observation, we need this data to help analyze it, which is what we did. So basically, in order for this ephemeral system to work, we have to give several parameters. And the first main parameter is a target object. And for us, this was the near-Earth asteroid 2003 SF84. And then after that, we have to have the observer location, which was the McDonald Observatory. And then for the time, we converted our observation times into Julian time. And basically, the Julian time system is a count of days, day 0, as noon on January 1st, 4713 BCE. And this number seems somewhat arbitrary, but it's set like that so that it's before any kind of recorded observations. So after we got this time, we had to fix our table settings. So basically, there's a lot of different variables that we can output, but we were mainly interested in these. Okay. So first we have RA definition, so this is just the celestial coordinates for the asteroid. And then after that, we have to know R, the distance of the asteroid to the sun, and delta, the distance of the asteroid to Earth. So we need these in order to calculate the difference between apparent and absolute magnitude caused by distance. And then after that, we have to know the one-way light time. And we use this to adjust our Julian time so that we know when an asteroid actually appears in space. So like, for example, if the asteroid was 1 AU away, it would take 8 minutes for the light from the asteroid to get to our eyes. So we use that difference to adjust our time. And then finally, we have to know the phase angle. So this is the angle between the Earth, the asteroid, and the Sun. So the asteroid, like our moon, has different phases. It doesn't always look like it's fully illuminated where we look at it. So in order, we need the phase angle to tell what kind of phase it's in so that we know what percentage of it's illuminated, and then we can calculate the difference in magnitude caused by the phase. So as you can see here, okay, so basically, like, once we get rid of all the photometric errors, we need to state it in order to get rid of the variations in magnitude caused by the phase and by distance. And then once we get rid of those, we can tell the fluctuations in brightness are caused by rotational period. So the reason the brightness fluctuates because the rotational period is because the asteroid isn't spherical, it's so long. So if we have asteroid Merkaba, it's not the one that we observed. This picture was taken by Japan's Hayabusa spacecraft, and you can see a shadow of the photon, which is pretty cool. So basically, as this asteroid rotates, like if the larger side faces us, then we'll see it'll appear brighter because a larger area will be reflecting sunlight. And then if like the edge faces us, there will be a smaller area facing us, so it'll look like it's not as bright.
Okay, now it comes to the fun stuff. Once we have all the data, we have to figure out what we're going to do with it. And as Maddie mentioned before, the atmospheric differences must be accounted for with the 25 stars that we had picked earlier. And this shows us, since everything generally moves the same way, stars, finding the magnitude of the asteroid versus the stars, you can really see the difference in brightness, which helps us find the overall rotation of the asteroid by doing something called the H&G system, which helps calculate the magnitude as a function of the angle, because as the angle changes, as the asteroid moves, the angle changes. As the angle changes, the magnitude changes. So we have to take all that into account and create a light curve, which helps us find period, fall orientation, and shape of the asteroid, but we only had enough data to use with it. This is the equation. It starts with two basic equations for h of alpha, which is the reduced magnitude, compared to h, which is the absolute magnitude. The absolute magnitude would come if the Earth were here. We observe the asteroid from here, which means the asteroid is 1 AU away from the Earth as well as 1 AU from the Sun. So the phase angle would be 0, but we can't do that, so we have to go backwards. So we start with the reduced magnitude, which is the apparent visual magnitude plus the differences in magnitude caused by R and delta. So using these two equations, we put them together, and this right here correlates to the distance magnitude, and this over here is the phase correction that's due to the angle. And then if you see the phi's, these are functions of the phase angle, this right here, and all these numbers are a constant that were created or observed by experimental analysis. So we plug in those numbers and we get a whole bunch of values for h. And then we use something called the Lomskargel method, which takes all the h values and makes a periodogram, which gives us possible periods. These peaks that we see, but are possible periods for the asteroid. And the program also gives us this line. You see it at around power of 11. And that's a threshold that basically says anything below that line is most likely not the period, by 99% not the period. So, but just to be safe, we analyzed all 4 of these. But as the program predicted, these 2 were a little more scattered than those 2. And you can see here, this graph represents this peak, and this graph represents this peak. And this one is a little higher, because the blue line is the data from the second night, and the red line is the data from both nights combined. So the blue one is slightly more accurate because there were more observations. So that's why this graph is a little tighter, like there's less scatter in this area than, as you can see here. But that alone won't give you the period, because that's only 180 degrees of return. Because as she mentioned before, when the asteroid turns, both sides are not equivalently shaped. So the brightness will change at 180 degrees. So you need to double this map and get something that looks like this. And these spots you see like around these places that don't really seem like they fit, that's just from noise that came from our data. So then after all of this work, we found that the 2003 SS-84 asteroid, nicknamed Rhesus species by us, has a period of about 9.7 hours with an error of about 25% of an hour for 15 minutes.
So basically, as you can see, there's a lot of math involved here. And so what Shayla explained is really our last step, and we only spent really like a couple of days doing this part. The majority of our work was spent analyzing a lot of data, like experience of it. And so basically that involved a lot of smaller, more simple calculations. And while this may not seem too difficult, because we were doing this like mainly with Excel, because we had more simple software, there was a lot of chance for error just because there were so many calculations. So basically what we did was we were split up into two groups, one for 1 day's observation and one for other days. And then we developed our own algorithms or equations to analyze the data, and then we used our own equations to check for other people's data. And this way we were able to get rid of more possibilities for error because it's unlikely that those groups would make big graphics.
So that's all, and we just like to thank the entire CSAT, especially Dr. Reese, for helping us make spreadsheets a little bit more enjoyable, which is very hard to do. And we'd like to thank literally all the scientists, all the mentors, especially the other interns here, UT, CSR, and NASA money. That's 2 weeks.
One right here.
Do you plan to formally submit that name to IAE?
We're not allowed to. You didn't discover it. You discovered it. Yeah.
It'll probably remain unnamed unless JPL's code gets sent.
In our heart, we will want to
Ask our project mentors to come up and give the certificates to the people on their team. I'll start with Aerospace Engineering, Dr. Wallace Fowler.
Come on down.
Aerospace Engineering, y'all come on down.
No, we knew there was one next to trackers. Like a new one, so we can name it.
We're going to do this
yeah,
in
we have
alphabetical order. Last name's me. Landon here first. Landon the food. Okay, next is Cameron. Cameron Bayhart. Brianna Cuero. Get up there. Okay. Jake Godby. And Diana Mesa. Run off about your stuff. Finally, the team lead, Paulina Demansky.
So, congratulations, Aerospace team. Astronomy. Okay, great. Dr. Petrie.
James Mitchell. Shaylee Patel. Maddie Springate. Peter Terraza. And Jasmine Wong. And let me tell you, they did a wonderful job, and they didn't even tell you that they had an extra task. They had to compare their rigorous reduction of data to my kind of quick and dirty, just look at the catalog thing, and I have to admit theirs is more precise. So thank you guys very much.
What do you guys think?
We're going to go to the break my fingers, not easy thing. Sonia, please,
Putting out the glasses and the words.
They'll miss the crib.
I don't know how.
All right, Jill, all right. Max Bowman. Annalise Goldman. Sonia Ingieri. And Rachel Penner. One thing the ICESaT team did not say during the presentation was their team slogan. You want to say it now?
It should be working, but it's not, and I don't know why.
Thank you, ICESaT.
Lunar Exploration, Addison
Okay. Casey Tobnos from Adrian Garza. Charlie Graham from San Jose, California. Eddie Harwood from Knoxville, Tennessee. Izzy Torres from Seattle, Washington. And Phoebe Wall from Redmond, Washington.
Our next group is the Magic Emergency Preparedness. Okay, Valerie and San Diego.
Do you know what we're talking
And then we have Lee Fleming. Sarah Kamaya from Dearborn, Michigan. Richu Mohaka from Florida. Sam Mosby from Van Alpine, Texas. And Jennifer Terry from Houston, Texas. Great team. Sorry, where's the bus driver? Thank you guys, and next time there's an emergency, I will call you. I'm in the middle of a presentation. Yeah. So Fred Porter with the Magic Flood Response Team.
I'll be cooking through. Alex Lloyd. Aaron McNulty. Leah Amstead.
I just want to say thanks for all your hard work, guys. It was, you know, I know that it's kind of challenging to do what we were doing, digging through that code and trying to learn new programming techniques and stuff. But it was really fun watching you guys get excited about it and really when the lights turned on and you kind of got it. That's something you were working hard at and you solved it. That's kind of what really makes it also fun for me too. So thanks.
for the Moon team, and Tom Ramirez is going to present those awards for Dr. John Brenner.
Wait, let's do it like quickly. Yep.
Shara Allen. Prachi Adam. Sebastian Perez Lopez. And Maya Taft.
Tom, Dad. Do it.
Do it.
Do it, Rusher.
So here is the audience, that was one of the RAs that stayed with the guys in the dorm, so they all know him very well. So thank you all for coming. It's been an amazing 2 weeks. We have wonderful opportunities for the C students. Please keep in touch. Let me know where you're going to college, what you're planning to do, and if you need a letter of recommendation, please reach out to either me or your science mentor. And we are going to close with a video highlight of the 2 weeks that you were here.
Oh, you guys are mean.
Oh wait.
I don't know, but I'm already crying.
He really does.
Wait, so don't get pictures.
I really do.
So don't get pictures. I've got some pictures on.
It's
I should tell you that the University of Texas Center for Space Research is part of the Cockrell School of Engineering here at the University of Texas, and Texas Space Grant is part of the Center for Space Research. For those of you who are from out of state, there is a space grant in every state in the United States. We are a line item in NASA's budget. If that gets back in NASA's budget.
We got it back in. One more year.
And it's back in the budget for at least for 1 more year. I'm just encouraging you to reach out to your space grant because each state is mandated to give $100,000 for fellowship and scholarship, undergrad and grad students in STEM education. So I encourage you to apply, and you would apply in the state where you're going to college. Okay? So here we go. Highlights of your 2 weeks here.
Oh, no.
It's amazing. Did you find it?
Oh my God.
Oh, we decided to. It's so cool.
I'll go the rest. 45 seconds. That was so good.
Not there.
I'm so glad it was that way though. And
Oh my god, I told you how to get this. I was like, I got A's. Every time I got F's.
why would you bring this up?
Yeah, because you guys there's two of them. Yeah, where's the
Yeah, I don't see a rocket.
Oh, is that there gonna be one the rocket one?
Why did I do that? Just like the solar, the solar
Charlie! Where's Charlie? Oh wait,
Where's
Norman!
I can't even see the space.
You see the frustration? Oh no. That's my cue.
Ian, what a baby.
Why am I talking?
Oh, yes. That's older. Yes. Oh, look at me.
Are you in there?
So there's one last thing that I'd like for you to do. There is a lady, she's the one that does all of our graphics. She has maintained the UT box. She's the one that was responsible for getting all the components together for your application for the judges to review. And she is not here, but I want, on the count of 3, I'm going to video you, and I want you all to say, "Thank you, Angelica." Okay, are you ready?
Yeah.
Okay, on the count of 3. 1, 2, 3.
Thank you, Angelica.
And she is the one that uploads all of the photographs for you to be able to access all your iFly videos, all of those things. So please join us outside for some brownies and lemonade. And the bus will be here at 5:15.